Okay, these are the notes for PreCalc, section 3.5. We are shifting our emphasis here to solving equations, both exponential and logarithmic ones. We will be looking also at Newton's law of cooling. All right, so first issue is we have some one-to-one properties. It says for any exponential function, f of x equals b to the x, if b to the u equals b to the v, then those powers have to match. In other words, if you have something raised to a power and the same base to another power on the other side, those powers have to be identical. For log equations, if the bases are the same, the log of u would have to equals the log of v, then u would have to equal v. All right, so we have three methods that we're going to look at for solving exponential equations. The first one is to get common bases. The second is to take the logarithm of both sides and expand it. And the third method is to use factoring and solving quadratic techniques. So the first one, getting common bases. We're looking at trying to convert the given bases into a common base on both sides. So since we're looking at 9 and 27 as our bases, we would convert those to 3s. So think of 9 as 3 squared, and it is to the 2x power. And think of 27 as 3 cubed, and that is to an x minus 1 power. And now when you have a power to a power, you just multiply them. So this becomes 3 to the 4x equaling 3 to the 3x minus 3 if we distribute that. And again, if the bases match, then the powers have to match. So we simply have the equation 4x equals 3x minus 3. Getting our x's combined, we get x being a negative 3. All right, for our second example, I'm going to get rid of that 20 so I can just deal with the 1/2 to a power. So I'm going to divide both sides by 20. We now have 1/2 to the x over 3 equals 1/4. And again, if we're trying to get common bases, we can think of that as a base of 1/2. So we have 1/2 to the x over 3 equaling 1/2 squared, which means x divided by 3, our power, has to equal the power on this side. So x would have to be 6. All right, this one is a little more involved, but we can still convert it to having common bases on both sides. Since we're dealing with numbers like 4s, 16s, 8s, we're going to use a base of 2. So we can think of 1/4 as 2 to the negative 2 power. We can think of 16 as 2 to the 4th, and then it is being cube rooted, so that would be 2 to the 4/3 power, and it is raised to another power of x plus 4. On the other side, we have an 8, which would be 2 cubed, and it's being 5th rooted. So we have 2 to the 3/5 power divided by a 2. All of that is to a 2x minus 1 power. Now we need to clean this up a little bit. So let's go ahead and distribute on the left here the 4/3. So we have 2 to the negative 2 times 2 to the 4/3 x plus 16/3. On the other side, inside parentheses, we can think of that as 2 to the 3/5 over 2 to the 1st. Subtracting those exponents would give us 2 to the negative 2/5. And again, I'm going to have to distribute those powers. So we're going to have 2 to the negative 4/5 x plus 2/5. On the left side, we could combine these. We have two bases here that are both 2's, which means we can add the exponents. We can think of this negative 2 power here as being negative 6/3 and combine it with the 16/3 that we have here. So we end up with 2 to the 4/3 x plus 10/3. All right, now we have a common base on both sides, which means the powers have to match. So 4/3 x plus 10/3 has to equal negative 4/5 x plus 2/5. And to solve that, since we have two different types of denominators and lots of fractions, let's go ahead and multiply everything by the LCD. We have a 3 and a 5, so we're going to use 15. Multiplying that, 3 goes into 15 5 times, so we get 20x. 3 goes into 15 5 times, which gives us a 50. 5 goes into 15 3 times, so we have negative 12x. And 5 goes into 15 3 times, so we get a 6. All right, simplifying, we can add the 12x to the other side. We can subtract the 50 to the other side, and then simplify. So 44 over 32, we could reduce that down to negative 11 over 8. All right, so that was the first method, getting both sides to have common bases. Obviously, that last question here was quite a bit more difficult, but just looking at all the different algebra that might be involved in these. All right, the second method was to take the logarithms of both sides and expand, and we can use logs with any base. Sometimes we'll look at the base and say, well, if we have a base here of 3 being raised to a power, let's use log base 3. So if we take log base 3 of 3 to the x, on this side we have to do the same thing, log base 3 of 11. On the left-hand side, if our bases match, we just get our power, so we end up with just a plain x on that side. On the right side, we have log base 3 of 11. We can use that change of base formula and just do log 11 over log 3, which ends up being 2.183. Now, we could have used a natural log as well, so I'm going to squeeze that one in here. If we take the natural log of both sides, then we would think of that expanding idea of when you have a power, you can multiply it out to the front. And then we can just divide the natural log over. So we're ending up with the same idea of taking the log of 3 divided by the log of, the log of 11 divided by the log of 3. It's going to give you the same decimal that we had here. It's just a different base. All right. For this one, since you have an e in the expression, I would use a natural log. We're going to divide that 9 to the other side, so we have e to the 2x equaling 30/9. We can reduce that to 10/3. And then if we take the natural log of both sides, on the left side, we're taking the natural log of e to a power. We just get the power. So we have 2x equaling the natural log of 10/3. And then we can use our calculator to find the natural log of 10/3 and divide out our 2. Now, simplifying this, we have some different options. That might be one option. If it was a multiple choice question, there might be other versions. For example, I can think of this as 1/2 times the natural log of 10/3. I can put that 1/2 back as a square root. So just a couple different options that you might see. Any of those would be fine as an answer on the test. All right. The next example, we have 7 to the x minus 5 equaling 2 to the 3x plus 4. Neither one can be written with a common base. 7 and 2, there's no base that would be common for those. So we are going to use that technique of taking the log of both sides. Again, it doesn't matter what base you choose to use. I'm going to just use a natural log, base e. So we've got the natural log of 7 to the x minus 5 equals the natural log of 2 to the 3x plus 4. We are then going to take those powers and expand them to the front. So we have x minus 5 times the natural log of 7. And on this side we have 3x plus 4 times the natural log of 2. Distributing, we've got x times the natural log of 7 minus 5 times the natural log of 7. On the other side, we get 3x times the natural log of 2 plus 4 times the natural log of 2. And then what we want to do is we want to get any terms that have an x in them to one side and any terms that don't have an x to the other side. So we've got x natural log of 7. I'm going to bring this one over here, negative 3x natural log of 2. I'm going to bring this one to the other side since it doesn't have an x. And then on the left side, we can factor an x out of everything. So we have the natural log of 7 minus 3 natural log of 2. All right. Then we can divide what we have in parentheses here on the left to the other side. So x equals 5 natural log of 7 plus 4 natural log of 2 divided by the natural log of 7 minus 3 natural log of 2. And now we're going to condense that. So those numbers that are in front can go back as powers. So this becomes the natural log of 7 to the 5th plus the natural log of 2 to the 4th. On the bottom we have the natural log of 7 minus the natural log of 2 cubed. And then we can condense it further. So x equals the natural log of 7 to the 5th times 2 to the 4th over the natural log of 7 divided by 2 cubed, which would be 8. Okay. If you had to give a decimal approximation for that, it should come out to be negative 93.627. But typically we look for more exact answers, so I'm fine with you leaving it without converting it to a decimal. All right, I don't have enough space for that next one, so I'm going to shift pages here. This time we have 3 times 5 to the 2 at minus x power, and on the other side 4 times 6 to the 1 plus x power. Again, we're going to take the natural log of both sides. All right, then we can expand those sides. So we have the natural log of 3 plus the natural log of 5 to the 2x minus 1. On this side we have the natural log of 4 plus the natural log of 6 to the x plus 1 power. And then we're going to bring our powers in front. All right, and then we have to distribute. So we end up with 2x natural log of 5 minus the natural log of 5, x natural log of 6 plus the natural log of 6. So again, we want to get anything that has an x onto one side and anything that doesn't to the other side. So I'm going to leave the 2x ln 5 on this side. This one's going to get moved over, this one's going to get moved over, and this will get moved to that side. So minus x natural log of 6. We have a negative natural log of 3. If we bring that over, we have a positive natural log of 5, and we already had a natural log of 4 and a natural log of 6 on that side. All right, factoring out our x. On the other side, we can condense that. We've got the natural log of 3 being minus, we're subtracting that, which means it's on the bottom. But the top is going to have a 5 times 4 times 6 all over 3, if we condense that down. All right, so we can divide or condense. Let's go ahead and condense this side a little bit first here. So we have x times the natural log of 5 squared, if we put that 2 back as a power, and the 6, since it's subtraction, condenses into division. On this side, if we take 5 times 6 times 4 divided by 3, we get a 40. And then we can divide this piece over. So it's going to be the natural log of 40 divided by the natural log of 25/6. And again, that would be your exact answer. I'm fine with you leaving it just like that. All right, the third method that we are going to look at is using factoring techniques or other types of solving quadratics. First thing I would do with this one is I would get rid of the fraction. I would multiply that denominator to the other side. So I'm going to have e to the x equals 5 times e to the x minus 1. I'm going to go ahead and distribute. And then I'm going to get everything onto one side, all my e to the x pieces. So I'm going to subtract the e to the x and make this 4e to the x, and I'm going to bring the 5 to the other side. And then I can divide out my 4. And then I can take the log of both sides, and since I have a base of e, I'm going to use natural log. So the natural log of 5/4 equals the natural log of e to the x, but that just simplifies to be x. So my solution is the natural log of 5/4. And again, I'm okay with you leaving it that way. You can expand it and write it as the natural log of 5 minus the natural log of 4. Again, if it was a multiple choice question, be willing to take either of those answers. All right, our next one, we have x's of some sort on both sides. We have e to the x's on both sides. So you don't want to divide out a variable. We don't want to ever divide out something where there's an e to the x or just a plain x, because we lose possible solutions. So let's get everything to one side and have a 0 on the other side. So we have x squared e to the x minus 3x e to the x. And then let's factor out our e to the x, since they both have that term in common. And then within those parentheses, they also have a common x that we could factor out. And then we can look at that zero product property, that since we have 3 different products here, any of them could be 0. So we're looking at when e to the x equals 0, we're looking at when x is 0, and we're looking at when x minus 3 is 0. So this one we can solve and just say x could be 3. This one we can say x could be 0. But if you think about your e to the x graph, if we graphed that exponential function, e to the x, it's always above the x-axis. So there's no place, there's no x value that's going to make e to the x equaling 0. So this would not give us a solution. All right, the last two that we're going to look at today. Again, more solving, looking at it in terms of those quadratics that we've looked at how to solve. So on this one, I'm going to bring everything to one side. Actually, let's start a different way. Let's take this e to the negative x and think of it as an e to the x on the bottom. Let's get rid of that negative exponent. All right, and then since I don't want to have my variable in the denominator, I'm going to multiply everything by e to the x. So on the first term here, we end up with just a plain 3. On the second term, we have a negative e to the x times e to the x. That means we're taking e to the x and we're squaring it. And on the right-hand side, we're going to have 2 times e to the x. All right, now let's get everything combined. I'm going to move that e to the x that's squared to the other side since it's already got a negative sign on it. I'd prefer to have that be positive. Okay, so we have e to the x being squared that we've moved to the right-hand side. We have a 2e to the x, and we're going to bring that 3 over as a negative 3. Now, e to the x squared is really just e to the 2x. So if it helps you to think of it that way, we can rewrite it. And what we have is we really have a quadratic equation, or an equation in a quadratic format. So we can factor this. Since we have e to the 2x, we can split that up and say we have an e to the x times e to the x. We are looking for two numbers that multiply to be negative 3 and add up to 2. So we're going to have a positive 3 and a negative 1. And then we're going to set each of those equal to 0. So when does e to the x plus 3 give me a 0? And when does e to the x minus 1 give me 0? Here I've got e to the x having to be negative 3. Here I have e to the x being a 1. Now, we talked about this on the last example. E to the x can't be negative, so this is going to be an extraneous, it doesn't work. We can look at e to the x being 1. That means x would be the natural log of 1 if we take the natural log of both sides. But the natural log of 1 is 0. So our only solution to that one is x equals 0. All right, our last example. I am going to move that 2, multiply it to the other side, but notice I do have a negative x power on that second e. So we've got e to the x minus e to the negative x equaling 10. And e to the negative x is 1 over e to the x. So I have that e to the x in a denominator position again. I'm going to need to multiply both sides by that denominator to give me an equation that doesn't have fractions in it. So now I have e to the 2x again, e to the x times e to the x, minus 1, those e to the x's drop out, equaling 10e to the x. All right, let's get everything to one side so we can try to factor it. All right, so we're looking at e to the x squared minus 10e to the x minus 1. It is not factorable the way it is. So I'm going to make this a little more simplified. Let's think of e to the x as just a variable. Let's just convert it. Let's say w equals e to the x. So we're looking at w squared minus 10w minus 1. And we can either do the quadratic formula, we could complete the square. Let's go ahead and complete the square. W squared minus 10w. I'm going to bring the 1 to the other side. I need half of 10 squared, so I'm going to add 25 to both sides. So I have on this side w minus 5 squared equals 26. Square rooting both sides. So I've got w equaling 5 plus minus the square root of 26. All right, now, I'm out of space here, so we'll move down. We had let w right here. We had set w as e to the x to do a substitution, so we could think of it in more of a quadratic format. So now we have to say, well, if w equals e to the x, then e to the x could equal either of these. 5 plus minus the square root of 26. Okay? So let's solve e to the x equals 5 minus the square root of 26, and e to the x equals 5 plus the square root of 26. The square root of 26 is going to be bigger than 5. So if we take 5 minus the square root of 26, that will be negative, which means we can't do this one. Okay, so that is not a viable solution. On the other side, though, 5 plus the square root of 26 is a positive value, so we can take the log of both sides. And on the left side, that just simplifies to be x. And again, I'm fine with you leaving it like that. That's an exact answer. If it did ask for a decimal equivalent, checking your calculator, you should get about 2.312. All right, and that's it for, excuse me, that's it for our first day of notes. We are going to spend 3 days, I think, on this section by the time we can get through everything. All right, so I'm going to have you go ahead and do those. Your homework then would be page 300, 1 through 6, 11 through 16, and 29 to 34.